Okay, hi, great, just on time. All right, so why don't I get going with introductions? So great, many thanks for those of you in person and online to make it to the talk. So yeah, delighted to introduce Professor Juan Wachs. And so he's professor and faculty scholar at the School of Industrial Engineering at Purdue University. And so, yeah, he's visiting Vancouver here for MCAI in addition to other things. So MCAI, as you might, as many of you will probably know, is the Medical Imaging, Computing, and Computer-Assisted Intervention Conference. And so there's about, I don't know, 1,500 people or so in town for that. And I think there's one more day and it wraps up. Yeah, so, and Professor Wachs, he's an associated editor of many IEEE journals and also for ICRA. Has his team has won numerous best paper awards, and most recently he's actually doing a lot of work as program director for NSF programs related to robotics. So that's quite a big role, I'm sure, and keeps you plenty busy. And as you'll see, his work in, among other areas, is in the area of human robotics interaction and surgical robotics. And so we have an intriguing title, Gore robots from blood and guts to bits and bytes. So welcome, Juan.
Thank you for inviting me. And really, it was the first time that I go to see the city from the hotel to campus. You know, I was able to see through the windows, and you have such a beautiful, sights and nature here. That is incredible. So thank you for the invitation. So yeah, let's get started. Indeed, I'm going to talk about robotics, and I'm going to talk about augmented reality and AI and a lot of good things. All right. So I like to start this talk by looking at how surgery was done. Basically, when you look at 200 years, more than 200 years ago, and the changes that we have gone through. In the beginning, you can see that, for example, surgery was taught in the operating theater, and the word operating theater comes from the fact that these auditoriums were actually theaters, right? And you see that it was a lot of touch, sense, feel, and see. And of course, when you look at this is a painting of 1882, just 10 years after, we have a different painting, show us the same or a similar operating theater, but with a few changes already. So what are those changes? You can already see that people are wearing white gowns as opposed to the previous one where people were using the regular attires to interact with patients, right? So they came to, of course, they start realizing that there are a lot of factors that start affecting the spread of infection. And one way that they have to avoid this is to change the practices, how people practice and how they teach and how they learn medicine. So, for example, using white gowns, they realize that they can see the body fluids like blood, and also they would change that from the regular attire, so they avoid with this spread of infections. But when you look at what surgery looks today, I mean, it's incredible. It's a shocking revolution. You see that it's all about computers and robots and monitors, and in fact, you wonder where the patient is, right? You can barely see the patient. I actually like this quote that when we look into medical education nowadays, know anymore about blood and guts, it's about bits and bytes. And I like, we have this cartoon here where you see how surgery looks today, all screens, monitors, robots, no one is actually looking at the patient, really. I mean, we all care about patients, but there is some interaction that is missing, right? So intuitive or naturalness that we don't see here. So something that is missing, you have, for example, these interactions that oftentimes happen with a regular team, which happens, for example, when you pass surgical instruments, or when you interact directly with the patient through, a open surgery, for example, or you interact directly with the surgeon, with the patient, you actually ask the patient how they feel. We are losing more and more that through the use of these technologies. So really, I'm very interested on trying to understand where the human is in this process, right? And I'm trying to bring the human back because I do believe that the humans and the experts in this case have benefits, direct benefits to the outcomes of the procedures. And bringing this expertise and the humans back is not a trivial question. There are a number of challenges associated with that. First of all, working with robots in close quarters is not easy. You see, the robots are bulky and it can be very dangerous to work in the proximity of these robots without proper safety measures. There is a lack of presence, of sense of presence, right? Because how we can be in person in a surgery where is right now surgeries are done through teleoperation. And the know-how of surgery that was learned and acquired through hundreds of years of the knowledge of medicine in a way is being transformed by a new form of medicine, if you want, which is done by machines. So how we transfer that knowledge? So I'm going to address these questions through a number of projects that I'm going to introduce here and try to see if we can answer some of these questions. So the first project is See What I Do. It's about the STAR platform. This was a collaboration with some folks at the Purdue University in computer science, folks from Indiana University School of Medicine, and some folks from the military, from DoD, that helped with a project that we basically were wondering, how do we do to transfer expert knowledge from surgeons, for example, to the field where you don't, in the field, you may not have that availability or that expertise, right? So is there a way to use information technology to transfer that knowledge? Let me show you a video, we'll see how that works. That highlights that. Okay.
All right, picture the area. Nurse, coming in with a blast injury. Right shin swelling quickly.
I'll prep him for surgery.
He couldn't use his leg.
We can contact our mentor stateside.
Hello, this is Dr. Anderson. My patient was caught in an IED blast. His shin is swelling. He seems to be in danger of developing compartment syndrome. We need to do a fasciotomy. Don't worry, I'll walk you through it.
He's ready for surgery.
Send me the data. We'll make 2 incisions. The lateral incisions will be made halfway between 2 compartments. Size of this line. Now we're going to make follow the order, right?
So let's move this forward. In the end, they say sedation, and as you can imagine. So this idea that you see was the first concept for the telementoring system. As you see in the video, we use a tablet as the first concept, and the idea is you have on the top left a group of experts that can work on the planning, and they can discuss what are the best steps to take for a certain surgery. You have a projection of the patient from a remote site. On the top right, you have actually could be a trainee on a surgeon that needs to perform the procedure, And in this case, we're using a tablet in the first concept, where in the tablet on the top right, on the bottom right, you can see you were able to actually see through annotations, arrows and polygons, what the medic needs to, what the surgeon needs to do, what are the instructions that she needs to follow. And there were options to actually see the previous steps and see what will happen next. And we tried this the first concept, we tried that on the atom, was at Indiana University School of Medicine. The atom class is the Advanced Trauma Operative Management course. It's a training course that residents need to take basically at some late stage in the residency program, where they are paired with experts, mentors, on different stations, and they use porcine models, and they recreate certain conditions that occur to patients. So instead of patients, they have porcine models, and they call the residents and they pair that with an expert, and they say, well, we have here a 25-year-old male with a gunshot on the stomach. You need to check what's going on, you need to deal with this. And of course, the residents need to start exploring what's going on. They need to, whenever they see an artery that is ruptured or anything, they actually need to treat that. And then of course, once they succeed, they leave the room, and the experts inflict a different injury to the porcine model and have a different condition to a new patient, and they call the resident again, and of course the injuries are progressively done on the porcine model until they get to the last one, which actually they do a direct injury, a direct blast on the, representing a blast on the heart, and the heart starts basically pumping blood. It's extremely stressful for the residents to be able to treat that, as you can imagine. Here we have some videos. Here is the expert. So this is basically a system tested on a fasciotomy on a porcine model. Usually you will not do fasciotomies on porcine models. This is something that doesn't really happen. Usually actually fasciotomies are practiced, if you want, on cadaveric legs, but this was as part of the atom class. By the end of the atom class, since the porcine models were available, we're allowed to try this telemetry system. And this actually, we're able to test it and see how well the main trauma surgeon was able to deliver instructions to the resident. And then we also tested how well these work when you look into, for example, interacting with the large interaction table on the top one, or the bottom one actually uses a group that are interacting together to collaborate in this surgery. So this was useful for us. So this was useful for us to try to understand how they interact with the virtual patient. If you want, as you notice, one of the things that we notice is they use real instruments, and they lay on top of the table, and the interaction table. We were able to capture those instruments through cameras and generate a virtual representation of those in the remote side. So, but just understanding how they work together was a very, I would say, enlightening experience, because we're able to modify the system according to what we see. Of course, one of the things that we learned through these experiments is that the tablet was standing on the way between the surgeon and the patient, and they had frequent collisions. So that didn't work very well, right? So we switched to an augmented reality glasses, the HoloLens, that was the HoloLens 1. And we actually tried this system in fasciotomies on cadaveric legs, where you see you had the mentor on the left side, the mentor was able to create annotations, and then those annotations were generated on the view of the trainee or the resident or medic, and they follow those annotations throughout the fasciotomy procedure. And this actually worked pretty well. We were able to mount the camera on the surgical lights, and the view of the patient was transmitted to the expert, right? But one of the problems is that, of course, when you look into field procedures and field surgery, you don't really have surgical lights. You need to find a way to have a camera, top view camera, somehow fixed somewhere to be able to transmit the images of the patient. So we thought that this is actually a great idea or great possibility to use robots, right? To use drones that they could be hovering on top of the patient, capture the top view of the patient, send a close-up image of the patient to the experts. The expert would have those images and operate based on the views, right? And then, of course, that will be generated on the medics. But you see, one challenge here is that, let me show you how this looks first of all. So, you have the drones hovering, as you can see, they take off, they go to the side, they try to hover in a stable position, they send the images to the expert that is in the bottom right, and then the expert generates these annotations, polygons, and also a combination of virtual instruments that are generated in the view of the medic, right? So you can see both the real and virtual instruments. But one problem that we notice is that having the drone hovering on top of the medic and the patient is, if you're really in a situation of an armed conflict, this will flag the position of the forces to the enemy, right? And that's actually not a good idea. So we actually have to find out a way to come up with a solution that would involve only the HoloLens. And, the HoloLens actually has cameras that you can use to capture the view of the patient. Now, the problem is you wear these cameras every time that there is a distraction, that the medic is looking somewhere else. Those images are sent to the expert, and the expert gets motion sickness, right? Because you're looking everywhere. So we have to come up with a way to stabilize the first view. And the basic concept is anytime that you're actually not looking at the patient, those are views or images that we actually don't consider. We only update the model of the view of the patient when the medic is actually interacting directly with the patient. Let me see, this work was covered. Let me show you how we actually tested this.
They often need to be airlifted or transported to facility, typically taking several hours. Dr. Juan Wachs is an associate.
Let me show you how this looks actually in a simulated setting, where we really use stressors to put the medics, under stress and see how actually they can perform when we simulated the sound of bullets, blast, explosions. And in this case, the medic had to conduct a crime. And there was, of course, also a trainer that is standing on the side, putting a lot of stress on the medics as well. And this was one of the validations, right, in how well this telementoring system would work when you apply in the field. All right, so of course, there are other things, interesting things that we could do with this augmented reality system, but this is just something very experimental and mostly for fun, basically based on external view of the patient, you can actually make some kind of, you can try to make an inference of what could be the pathology of the patient. So of course, this is not an X-ray, this is not precise in any way, but this is more something for us to speculate about and how well this will work. At least it can teach you something about the anatomy training. Right. Okay. Of course, there is a question of, how do you deal with, how you do this telementoring when you don't really have a medic, or when sending a medic to the site, it could be extremely dangerous, right? So this is exactly the occasions when we start thinking of robotics. This was a collaboration with people from Johns Hopkins, IU School of Medicine, telemedicine, the Department of Defense, the telemedicine branch, and a number of other people. And really what we wanted to look is if we really have a challenging environment, challenging setting, how we can use robots to send them to the point of injury and how they can help to actually treat a patient. Remember, most of the use of robotics up to now is in a controlled setting, in operating rooms where you have control about everything that is around the patient, right? So the problem becomes really challenging when you need to really go, rather than bring the patient to the site of surgery, send a robot to operate. And there's a number of interesting questions here. One is, we can always try to we can always try to use these machine learning techniques to train robots to do procedures, but you need data, right? And there is a lot of data from the operating room, but there is virtually nothing related to stabilization treatments and surgeries in the field. So, one question was how we actually can transfer the knowledge, how we can transfer the skills from the control setting to uncontrolled setting. The other is we want to come up with a way that can be usable for a number of robots. We don't really know how these deployable robots are going to look like, and not something that can be generalized. And third, you want to create a skill, a library of different skills, because you want to be able to treat a number of conditions. So, the concept that we thought about is to avoid the delays and this disconnection between the reality of what is happening in the remote site and how you operate, and how those delays can affect the outcomes of the patient. We decouple the two processes by creating a virtual environment where the main surgeon operates, but that virtual environment will give real-time information about the most critical aspects of the patient and the vitals. And then what we will do is we will let the expert operate, would capture the maneuvers and convert that into high-level activities or actions. We call that surgeons, and send the surgeon information to the remote robot, and have the remote robot figure out how to decode the surgeons based on the current context. So that's in a nutshell what actually we did. But again, we have to deal with the problem of training. So what we did was we collected a little bit of real data through simulation, and then we simulated data that we augmented on top of the real data, plus the addition of data from the operating. And we combine all these data sets to train machine learning models to be able to recognize and predict these routines that we done. We use the Taurus robot, which is a tiny robot that actually can be deployed. This was in collaboration with SRI. And again, in order to generalize these routines, what we did is we use a number of robots. Some were simulated robots, some were real robots, always looking at two-arm robots. We tried to learn both the physical appearance of the surgeons and the kinematics. And we realized that the most important piece of information to be able to recognize regimes is the kinematics. Yesterday we had a few presentations at MICAI showing also recognition of robotic movements, and they actually reach the same conclusions that kinematics is the most crucial piece of information. So we look into these maneuvers, we classify them into regimes. In this case, we're looking into 7, for example, different regimes. We look into 2 different procedures that we use as demonstration cases for this example. One was a peg and pull transfer, and the other was a debridement. Okay, so one question that we also had is, can we also learn between procedures? Means, in other words, if we train our system on a peg and pull transfer, do we need to teach from scratch a debridement, or can we use a pre-trained system on a peg and pull to be able to use that on debridement with very little training? That was actually our hope at the end. So this is interesting. We actually found that when your system is, so there is no transfer at all, you train from scratch. Of course, the performance, this is the number of observations. With very few observations, the performance is low, and you need to get a significant number of observations to be able to get, up to 85% accuracy. Where when we use the transfer learning approach, in other words, the network is trained on a peg and pull transfer and it's doing very well on peg and pull transfer, you only need to give very few observations of the debridement to be able to perform relatively well. With more observations, of course, we do better. So it's an interesting concept that you don't need to train the system with all the possible procedures. We can actually use this transfer learning idea. So we actually conducted 2 demos. One was the peg and pull transfer, but to make our life more difficult, we actually immersed that in artificial blood. So that made, of course, the computer vision part more tricky. And as you see in the artificial blood setting, this looks more like a turbulent regime. And the surgical debridement, we had, we had these taros also. So in the left, we actually used the Yami robot from ABB, and on the right, we used the Taurus robot. And an interesting concept here is, in order to deal effectively with the delays, we created this phantom model, that the phantom model tells you where the robot currently is. So what you see in the virtual environment, you see the movements of the robot in the simulated environment. But remember that you send the instructions, the robot still needs to move. So what you see in yellow is the real state of the robot. And of course you have a gap. And having the operator be aware of this gap between the reality and what is actually happening and what he's performing in the simulation, it makes her aware of how to build or how to plan the next steps in the procedure to be able to make sure that there's no mistakes, right?
So you just by that gap is you just mean the time latency, or
the time latency, and the gap is because of the time latency. Exactly. That is expressed through again a visual.
Can I just ask what the action space is for this for the task? So you're commanding the kinematics.
Right. So we have 7 regimes, 7 actions.
Okay.
This and I think there were 7 actions pretty much for both, or 7 in one case and 6 in the other. I think that for the peg and pull transfer were 6 operations or 6 regimes, and for the surgical debridement were 7.
Oh, okay. So the action space is the specification of which regime to do next.
Right. Because basically the procedures share some common space, but also there is some space that they don't share because of the particularity of the procedure, right? So you always want to train the system for the largest space, which in this case is 7 regimes.
But the regime itself that runs autonomously, basically, or that's a separate.
The regime writes, so correct. So you send the regime instructions to the remote robot, and the robot needs to decode that searching based on the target and based on the context. With the target is part of the context, but the environment, the position of the objects, the obstacles, and because they are, remember that the simulation is some form a simplified version of what really happens. So the coordinates are adjusted according to what is really happening on the target domain.
Right, but the action space, if it consists of these surgeons, it is then discrete, right? Like it says, do surgeon 5.
Right.
Okay.
The action space is discrete as opposed to what we did later. Really later, we look into a problem. I'm going to talk about that potentially you can use to treat or to deal with any type of procedure.
Yeah. Okay. And the policy working with that action space, that's trained using supervised learning and imitation, or it's trained using reinforcement learning? Or?
This is using reinforcement learning, but based on the supervised set. In other words, the regimes were annotated and supervised, right?
Yeah. Okay. Oh, yeah, the question. Sorry.
Yes.
Just kind of follow up. So once you selected a regime, do you provide kind of high-level parameters to each regime, or is it just?
Right. It went the regime with high-level parameters, which were basically the position of the objects on the simulated environment. So that was sent. So this regime plus parameters, so the parameters would have to be adapted to based on proximity and face validity to the target location, right? So of course, that was all the information that actually was sent. Yeah.
So there's computer vision in the loop, both for the surgeon choice and for the actual execution of the surgeon.
Right. So for the surgeon choice, is mostly machine learning, because what you do is you acquire the position of the maneuvers through controllers. So you don't really need machine vision. I mean, we try interesting things. We also try things like touchless surgeries and movement of hand, gestures, and see how that would work. But eventually, what ends up is that the best approach was really use controllers like the ones that you use, for example, for the Da Vinci. So you acquire the coordinates and the movements of the hands, and you convert that, the kinematics, you convert that into regimes, and you send the name of the regime to the target domain. But in the target domain, you do need computer vision to identify, if you want, the registers, the same landmarks.
Right.
You show the simulation to the real setting, and to recognize the obstacles and recognize the targets as well. Okay. All right. Now I'm going to make things even more difficult. Now, in the beginning we have the interaction of the surgeons with the patients, and then we say we're going to move into a setting where we are going to decouple them. They're going to be located one far from the other. So we are going to use telementoring and telemedicine. And then we said, well, but now we cannot really use a remote surgeon because we don't have one, right? So we use robots. But of course, the robots need to have some level, if you want, of supervision. They're not completely autonomous, right? But if you don't have communications whatsoever, you don't really can teleoperate, and you cannot really communicate. So if there is no really communications whatsoever, you need to look into some complete or full autonomy setting. And so we came up with the idea of this AI telementor mentor framework, where we said, okay, so if we can give an AI system all the, we can teach all the possible procedures that it's going to see, and we caption. In every procedure, we look at every frame, every key point in the procedure, and we caption that with instructions, with what's going on. We can convert those captions into instructions and articulate that using verbal natural language to the medic, and this will serve as an artificial intelligent mentor. So we created a huge data set of procedures, and we trained a neural network, and we did was basically this captioning system that you see for every image here, you have a caption telling what's going on, right? And this work relatively well for some simple cases, but we very soon notice a number of problems. One is that when you look into mentoring, you need to tell the medic what to do next, not what he's doing now, because he knows what is he doing now, he's doing it, right? So you need to be able to anticipate the next action, not just to recognize the current one. Second is that you can have so many variations that it's really difficult to come up with a, so these generalizations work pretty well in control environments. But when you look into deployment, the variability is so high that, you know, the views are very different from the trainings that you get. So we come up, so let me just finish. So for the previous system, we really came up with the DAISY data set that is available online. It's pretty large. We have 290 different procedures of 20 medical disciplines, more than 17,000 color images, all with captions. And this is again available for the community to use. But really, in order to deal with activity, captions and static frames are not enough. So we have to really go to the problem of recognizing activity. And this is how we came up with the Thomson dataset and Thomson challenge that we are running right now in MICAI. So we're focusing right now on 5 procedures. And let me show you how the trailer for this looks like. Oh, wait a minute, I know it. I need to show the other screen.
Next. Take me.
Ready.
Right, so this is the challenge that we are running right now at MICAI. We are basically looking at videos, 5 different procedures, right? But what we are doing that is interesting is that we are, in this example that you saw, we are not trying to recognize the procedure. So there is no prior information about what procedures are given. The idea is that if we teach the system enough procedures, it will be able to generalize actions, which in this case, the actions are nouns and verbs, for any procedure that it may encounter. That's the basic idea. So if you are familiar with the kitchen and the EPIC, a challenge in machine learning where you are trying to recognize actions from several recipes that you see, the idea is that that will give you enough generalization to be able to predict or recognize any activity that involving the kitchen of a person trying to prepare anything, right? So we have specifically for the trauma Thomson that we're going to have that tomorrow, Thursday in the morning. It's called Trauma Thomson Challenge. We have 5 different tracks: action recognition, action anticipation, task recognition, and visual question answer. So Okay. So when we look into this artificial intelligence mentor, what we want to do is to be able to anticipate what needs to happen and convert that into language, spoken language, and be able to tell that the medic, do this, do that, right? But then again, there's a number of interesting things now that we have the data set. There's a number of interesting things that we can do. We can recognize what's going on, we can recognize the task, and we can ask questions about what's going on with the patient and train an AI system to be able to reply to it, right? So we come up with a data set, we annotated using natural language processing every segment of these activities. You see, as I was telling you, for each of these clips, we have annotations that are a combination of a noun and a verb. For example, insert, detach syringe, drop hook, drop obturator, compress unpack, and things like that. And this is how we refer to the actions that we use for training the system. But so it's an interesting problem, of course, because there are certain actions that you see a lot, and there are certain actions that you rarely see, and you still need to be able to generalize between different procedures, right? So if you look at the verbs and the nouns, of course, for the combinations that are very common, you're very likely to recognize that, but for those that have the frequency is very low, the frequency of occurrence of the whole action is extremely low. That makes the problem very challenging. We are doing other interesting things. We are modeling the procedure through task graphs. For every procedure, we are representing them into task graphs. And these task graphs allow us to use, for example, adjacency matrices with some variations because our graphs are cyclic. In other words, we may repeat certain steps. And with these representations, we can actually classify procedures based on distance matrices. In fact, we found that we can have different representations of these matrices by merging the repetitions or without merging the repetitions, and using, for example, Euclidean distance or Mahalanobis distance, and we can use that to recognize mistakes or to recognize shortcuts. Mistakes is something that you want to recognize, of course, because you want to be able to tell the medic that there is a mistake. But the shortcut is very interesting. It's maybe a creative way to solve or to treat a patient in a faster way. And you also may want to recognize those procedures because you can use that to actually assess performance, right? You can actually reward that type of behavior. So for action recognition, our baseline is we're using a relative vision transformer. And again, we're also doing action anticipation, use transformers as well. So these are the baselines that actually we're using for the part of activity recognition. Now, you see, as I said, the problem is quite challenging. We compare with other data sets, in this case, the Epic Kitchen and the GAZE. We also compare with different, we look into different procedures within the overall recognition. And you see that the average is, so for the verb and noun, this is, not ideal. Of course, when you look into action recognition, the accuracies go really low. And if you look at the top 5, of course, you go up, which is, if you are able to recognize the right answer among the best 5, that we consider a hit. But you see, this is pretty low, and that is why we thought that we need to have a challenge and to call the community to actually invite them to beat these results, because we need to see if there is a better way of doing it. So these are some examples of the action anticipation and action recognition. I don't have here the visual question answer, but I do have new slides that we're going to show tomorrow about that. And we're going to see tomorrow how the community is doing regarding beating these baselines. We got some interesting results. So some final thoughts. I do believe that the human element is not only a cessation, but it improves, it helps these cyber-physical systems. How to generate a sense of co-presence is a challenge, right? this generation of projections of human appearance may not be enough. You also may want to generate a sense of touch, and that's something we need to work on. You need the expertise of the people because that is what provides the context. And context, learning from scratch, context is definitely not easy, but also is a waste of resources. When I talk about expertise, I also look into human intuition. This is important, and we need to find a way to combine the human intuition into these expert systems. So thank you. I want to acknowledge my sponsors, and thank you for the invitation.
Great. Great, we have time for questions. I've got a few, if someone wants to jump ahead. Yes.
Yeah, so I'm curious, like, to what degree, like, thinking about a lot of the data sets that you have now and that you're generating, and like even on some of these transfer tasks, like to what degree some of these like pre-trained or foundation models are going to like come into play with the systems that you're developing?
Well, I think that foundation models is what I hope to see coming from the community. We're going to see some of that tomorrow. When looking into captioning, we're looking to visual question answer, when looking at action recognition and action anticipation, there is not really a point to train a different network to solve each of these different challenges. You really want a foundation model that can help solve all these problems together. And this is the direction that, in my opinion, we should go. Now, I don't know yet how well that is going to work. We're going to see tomorrow some interesting results of that. So, yeah. So you're invited to come to the MICA challenge.
I'll ask you a question about for the data of these given procedures that you capture. Do you make an effort to capture? I don't know whether to call them mistakes or completion conditions, because it, as with any task, figuring out when you've completed, a step with a sufficient degree of accuracy that you can proceed to the next step versus you maybe just making some adjustments again, et cetera. So how to I could see like a pure clean data set of how to demonstrate the ideal surgical procedure being different from a procedure as it happens in practice, because this thing slipped a little bit and therefore you had to grab this thing again. And so I was wondering if you could talk about kind of variation along
Definitely. So basically what you're talking about is how we capture really enough variability without. So I guess the big challenge that we're trying to deal with this data set is how to capture variability with the least amount of data, how to capture the highest variability with the least amount of data. And in a way, we want to be able to have more than 5 procedures, maybe 10, 20, 50, but maybe have only 1 or 2 observations done by different people on different settings with different instruments. And we're trying to move on the traumatons on data set. That was the guidelines that we used to collect data, but it's difficult because we are working with, basically our collaborators are from the Department of Defense, and the perspective is very different there. The perspective is we need to come up with a protocol. What are the steps? We all need to follow the same steps using the same tools. And it has been a challenge for me to convince them that no, the whole point is let's do not do that. You guys all know how to conduct these procedures, just do them. Oh, well, but that when you look at the tourniquet, you can do tourniquet with different tools or different, even the kits that the medics receive are different. And I'm like, great, do that in different ways. In fact, one thing that you can see that is interesting in the EPIC kitchen is they collected data sets from people cooking from all around the world. And why? Because the settings look extremely different. They cook using different techniques in different ways. So my idea was the same, look at how they do a tourniquet in Canada or the US and how they do a tourniquet in Israel. And let's try to collect all this data. But there is a reason why there is not much of this data. You have a lot of cooking data. You don't have a lot of medical type of data from the field. It's because there is a problem of identification of, making sure that they identify the data. And they're even concerned about recognizing tattoos on your hands. So it's getting to even conduct these on simulated patients is difficult. We're using, in most cases, mannequins, and the ones that you saw of tourniquets in the field are actually YouTube videos that are available. But we cannot really collect that data, that type of data. It's
Yeah,
really, we're
Yeah.
centuries away from getting to that point.
Yeah. And so, okay, so I hear you describing it as there's a gap between wanting formalized checklists, which the medical community loves because it does stop people from leaving tools in the patient and whatever, like
Exactly.
checklists, just like flight safety,
Yes.
your pilot to follow some exact procedure, and that saves lives. On the other hand, on the other hand, maybe in the real world, you don't always follow that checklist, and so.
Right.
So,
in the real world,
yeah,
the times that you really need to use these systems are situations where you may have not encountered before, you may not have the data before, and it may not even be useful. The correct protocol, given that you're in a limited setting with constrained tools, with constrained resources. If you don't have a rubber band to actually perform a tourniquet,
right.
and you have a T-shirt, you need to use a T-shirt for a tourniquet. So you need your system to be able to guide you under that new system, under that new environment. And that's, I think, a sweet spot where I would like to, where we would like to continue this work.
Other questions?
So very interesting talk, thanks. I have a question about kind of the variability on site when you're kind of deploying robots, let's say in the war zone, right? So you have a rover, I think it's in one of your slides, and it's kind of getting close to the patients or the wounded. What are some of the kind of the variabilities or dynamics that can happen? For example, let's say a bomb just went off close by, and there are kind of vibrations.
Right.
So are there other kinds of dynamics that will kind of come with it?
Right, anything. I would say anything can happen. You pretty much everything, and much more than what you mentioned. Therefore, we don't want to follow on this concept of high-level knowledge of what a robot needs to do. In fact, we're going in the totally opposite direction in the sense that, okay, what humans do, and let's try to learn from humans what robots need to do, rather, which is a top-down approach, rather the bottom-down, which is we have this Da Vinci robot, and this is the kinematics model, and they all need to move arm number 3 in this direction, because anything is bad. We can actually have every possible change there. So the only way to attack this problem is to have this high-level knowledge delivered to the robots in some way, and the robots need to figure out what to do based on their self-awareness of how their kinematics look. Every robot has a moment of that, or can have, and then being aware of the current context that they are situated, and analyze based on the context and the high-level procedural knowledge what needs to happen. They code that and have, if you want, intelligence to perform the executions in the right way, because you cannot really come up with one model of this needs to happen, assuming that they have this robot, because, we don't, to us, it was not even given what is going to be the robot that is going to be deployed if there's going to be a robot. That's the challenge,
I'll ask kind of a crazy out there question. So I guess in reinforcement learning, we're seeing lots of people learn how to play Minecraft from YouTube videos, etc. And so I guess I'll directly place that in contrast to serious stuff like medicine, and surgical procedures. And yet, you know, maybe there is something to be learned about, yeah, you know, how we can learn from others in the same way we can learn from Minecraft videos of YouTubers. Yeah, maybe if we have just access to a ton of surgical video, and that can be mine. But yeah, okay, there's
Honestly, not
Yeah.
much, and we have been working with, Johns Hopkins, with Gregory Hager there, coming up with a game, gamification of a suture task, really coming with a simplified version, creating kind of a game, an Atari game, and using reinforcement learning, because reinforcement learning with Atari is very doable. The training is very doable, and you can actually get to a very good performance, incredible performance. But when it comes to adapting that to reality, it's just not feasible because of the complexity of the search in three-dimensional images, right? So where with variable textures, when you don't really have objects that are rigid pieces. So, that's another basically insight, which is reinforcement learning is not something that we can use for this type of problems.
yeah,
We can use in the games, but we cannot really use in, if the setting is extremely constrained, and we have been doing this for the pagan pole and the rudiment, we have used reinforcement learning because the setting, it is a constrained setting. But as soon as it comes to something that it's a long horizon task, it explodes. There is no way that you can.
and good simulators for all of these tasks you're describing.
Yeah.
It sounds pretty hard to simulate all possible tourniquets and whatever. Or,
There is interesting work on simulating realistic models, especially for the Da Vinci. And there was a challenge I don't know if it was in the last MICAI or was actually in ICRA, about calling competitions for simulators for simulated anatomies and using the Da Vinci, which again is very, very not constrained, but it's very well controlled about how to train systems to perform needle passing and suture. And you can do that if audits are very constrained. You can do that. People have been doing these realistic models. It's just to be effective in an uncontrolled setting. That's not something that I haven't seen. Yeah, put it this way.
are there any questions online or? Yeah. Any last call for questions? Okay, great, many thanks. Yeah.